Okay, so in the previous class we were looking at we have defined this quantity called G mix, which tells me whether species 1 and 2 want to stay separate from each other, meaning do not want to interact with each other, right. So, I can put them together, but they hate each other so much like water and oil that they would not interact with each other, they will not mix with each other, they will not form a solution with each other. Okay. Or do species 1 and 2 actually, so once I put them in close proximity of each other, they will start, the process of whatever is the process, right. So, it can be diffusion, it can be whatever, right. So, that will be told by kinetics, but eventually does thermodynamics prefer that they mix, right. So, do the so in the analogy of a marriage, is there enough compatibility, right. So, is there enough agreement on both sides that once these two people marry, it is a compatible relationship. Okay. If thermodynamics itself says no, then there is no point mixing them, right. So, they will always stay separated. So, there is no point marrying them. Okay. So, what is the thermodynamic quantity that says that they can mix and form a solution? That is G mix, right. And G mix, so the negative of G mix times n, we have defined it as the driving force, because driving forces we wanted them to be positive. Now, if the driving force is positive or G mix is negative, so they would mix at that composition to form a homogeneous solution, right, and that has a certain phase, right. So, this is what we did, and we have developed enough language to understand so what this G mix is, and to understand the driving force, everything in the language of thermodynamics. Okay. By the way, you may want to realize now, I think so before I move much further, that when I keep using the word driving force, I am still looking at the energy, right. So, delta G's are still in units of energy, it is not really the units of force, right. So, in thermodynamics, that is the so unfortunately or fortunately, that is the difference from a regular physics definition of force, right. So, it is not a real force, but thermodynamically there is a driving force, meaning there is enough energy differential, right, that given enough time and given I provide enough so given that the system can find ways of going from one state to another state, it will, that is what it means, right. But it is the difference in energies between the two states, right. So, that is what tells me the driving force for the one state to go into another state, right. If the free energy of one state is state 2 is less than free energy of state 1, then eventually so assuming that kinetics makes it possible, a system will go from state 1 to state 2, that is what it means. Okay. So, it is not a real force that is forcing the system to go, it is telling me that look, the system actually wants to go there, and so the thermodynamic force, the driving force that you define in this context is different from the Newton's forces, right. So, the force that comes out of Newton's laws and things like that, right. For one, the units themselves are different, these are units of energy, that is units of force. Okay. All right. So, having said that, now let us look at all right. So, we have developed what G mix is, right. And we also said this, right. So, G mix is nothing but x1 times mu 1 mix plus x2 times mu 2 mix. Every time I write this, you may want to actually realize that mu 1 mix is mu 1 in the solution contaminated mu 1 minus mu 1 pure. Okay. Similarly, mu 2 mix is mu 2 in the contaminated form minus mu 2 pure, right. Okay. So, these are enough negative numbers that x1 times this is a negative number. Okay, good. Now, further to understand this G mix as a function of x1 and x2, right. So, and how do I get these sort of curves? I just said, right. So, in one of the classes I just said this is convex down, right, but in the last class I said all right. So, if it is convex up, then all my solution thermodynamics is going to go to hell, nothing forms a solution, right. So, how do I get this value of G mix, right. So, to get me a value of how G mix varies with x2, that is what I want to get, right. So, these are how do I arrive at these sort of functions or these curves. Earlier also, you see, if I just go back a few classes earlier, we were looking at how G varies as pressure, how G varies as temperature, right. Then we looked at the global P versus T phase diagram, right. And when we constructed the phase diagram, let us say so P versus T phase diagrams, so we said solid, liquid, gas, correct, and we said solid means the G of solid is less than G of liquid and gas, right. So we are comparing the G's. Solid, this portion belongs to solid means we are actually comparing the G's. Similarly, G of liquid here is less than G of gas or G of solid, right, and so on. So essentially we need information about G's to compare the phase diagrams and want to make the phase diagram, and G as a function of so here we said okay, so let us look at small g instead of capital G, and so when we are looking at composition, G as a function of x2, right. So we want to create these sort of curves, and for that we want to understand G as a function of x2, but we just wrote G mathematically as, or G mix in this case, right, as just mu1 mix plus mu2 mix x1 and x2, okay. So to understand G as a function of x2, right, so now we have to put in more material science. So what exactly is G as a function of x2, right. So for that I want to understand what mu1 as a function of x2 is and mu2 as a function of x2 is, right. So mu1 and mu2s are dependent on x2. Okay, all right. So I am going to now introduce the idea of what is called activity. Okay, so mu1, I am mu1 mix, right. I am going to define mu1 mix as kBT log activity of species 1, and mu2 mix is equal to kBT log A2, right. So activity of species 2 in the solution, right. So now AIs are nothing but what are called the activities, okay. So activity is nothing but it is a proxy for chemical potential, right. So I the chemical potential advantage I get by mixing, right. So activity AIs are nothing but they are proxies. Instead of saying oh this is mu1 mix, mu2 mix of mu I mix, okay. So I am just defining AI to be kBT log mu mu I to be kBT log AI, okay, mu I in the mix, right. So mu I mix, not mu I per se, but mu I minus mu I tilde, that is what I am looking at. Okay. So that is how I define the activity. So activity tells me about the driving forces for mixing, okay. All right. So essentially I want a relation between activities of species, right, A1, A2 and compositions, right, that is x1, x2. If I have that relation, I know that G equal to x1 mu1 mix or G mix, right, plus x2 mu2 mix, and G mix hence is equal to x1 times so kBT log A1 plus kBT may come out, that is okay, plus x2 times log A2, right. So still G mix as a function of x2 means I need to understand how AI is varying as a function of x2, A1 varies as a function of x2 and A2 varies as a function of x2. So I need information about activities as a function of x2 for me to completely understand G mix as a function of x2, okay. Okay. Now this should be a solution to solution dependent, right. So this should be right. So activity of water in water oil solution, will be something else compared to activity of water in water sugar solution, right. So, activities are going to be different, so depending on the system, right. So, every system goes by its own material science, every solution, let us say. So, activities need to be determined system to system, need to be determined on a case to case basis. Okay. But alright, so instead of doing case to case basis, let us look at some simple models, simple what are called solution models that relate activities to compositions, right. And later say so which and later say which materials which solutions come close to these simple models. Right. In general, our models are going to be complicated, every material has its own interactions and things like that, right. So, every material has its own interactions, so the models are going to be complicated, but let us look at some simple models, and based on these models we will look at what does this activity really mean, right. So, what is activity capturing, right. So, this will be this can be illustrated by simple models. Right. Once we understand the physics, atomistic physics of how so this quantity called activity is capturing, then we can so then you should be able to construct more complicated models that we will not look in this course, but so you understand at least the essence of these models. Okay. All right. So, the first model is what is called an ideal solution model. Okay. Now, in an ideal solution, I am just going to say that activity is the same as, now there is much more to what I am doing than just I am simplifying the simplified thermodynamics for you, right. So, there is more complication about how exactly to define activity, how to take this model, etc., the so called Raoult's law, the so called Henry's law and so on. Let's not do that in this course, right. So, because there is a course towards material synthesis, let us not make it a complete thermodynamic intensive course, right. So, let us take a bit off from thermodynamics, and whatever is important I am going to introduce that. Okay. So, whatever is not very much relevant to this course, I'll skip it. Okay. So, I am just going to say that activity of species 1 is just nothing but the composition of species 1, activity of species 2 is nothing but the composition or fraction, atomic fraction of species 2. Okay. So, this is an ideal solution. Let us look at what ideal solution means, right. So, first let us put it in the mathematics and then we will get a physical picture of it. Okay. So, now mu 1 of an ideal mixture now, right. So, it is not a mixture anymore, this is an ideal mixture, that is equal to kBT ln x1, and mu 2 of an ideal mixture is equal to kBT ln x2, right, and G of an ideal mixture, G mix, right. So, this is my driving force to form an ideal mixture, is mu 1 ideal mixture plus x2 mu 2 ideal mixture, and that is equal to kBT x1 ln x1 plus x2 ln x2. Okay. Okay, good. Now, let us draw this, right. So, now I have my first solution model where I can clearly draw G ideal mix as a function of x2. I exactly know the solution form, right. So, G ideal mix as a function of x2 is x1 ln x1, x1 is nothing but 1 minus x2, right, plus x2 ln x2, and this is dependent on the temperature at which I am looking at this, right. So, kBT times x1 ln x1 plus x2 ln x2, right. Now, this so like we said is going to be very symmetric, about x2 equal to 0.5, and so if it did not come out to be symmetric, it has to be. Okay. Let us say 1 and 2 are going to so if they form, they will form an ideal solution. We will look at what an ideal solution is in terms of what are the interactions between 1 and 2. Okay. But for now, let us say if 1 and 2 are an ideal solution, I have a form for G of ideal mix as a function of x2. I have a mathematical form, right. So, this is just x1 ln x1 plus x2 ln x2, all right, good. Let me ask you this question: what is dg by dx2 as x2 goes to 0, or dou g by dou g ideal mixture, or dou g by dou ideal mixture as x2 goes to 1, right. You can see that so the way you can plug it in this equation, right. So you can see what dou g ideal mix by dou x2 is, and as x2 goes to infinity, this is going to be so 1 of plus or minus infinity, right. So this has a slope that goes to infinity, this also has a slope that goes to infinity, right. What does it mean? This means that, look, let us say I give you material 1 and 2, sorry, I give you atoms 1 and 2, right, and I say that by no means they should mix, right. So by no means they should mix. I will ask you later, after 2-3 years of your PhD, I will ask you that to give me back the same pure compounds, the same pure materials, material 1 and material 2, or species 1 and species 2, right. If species 1, right, so species 1, how can it mix with species 2? It mix with an infinite slope, right. So even even if I put 0.00001% of species 2, the slope is just falling down. I mean, so the G curve is just falling down so rapidly with an infinite slope that so how much ever I try for it not to mix, it will start mixing. Okay. So that is why so if I have I say pure nitrogen gas, give me a pure nitrogen gas. What is pure nitrogen gas? Nitrogen, so there are all these other trace gases, right. So pure nitrogen cylinder, I will say that what is the purity? The purity is 99.999%, that is 3 nines, or this is called 3 nines, right, or 99.99999 that is 5 nines, right. I never get 100% pure, right. Why? Because it is always so if I am 100% pure, I am sitting at that cusp where I have an if I slightly add a small amount of impurity, it is just going to I am just going to come down from that cusp with an infinite slope, right. So for me to maintain that purity is very difficult, because my slope of coming down out of that purity is infinite, correct. So as a result, one can always make this statement, right. So this is in case of an ideal mixture, but an ideal solution, but in general also this is true, that pure compounds almost never exist. Okay, I will write almost, but I am sure they never exist, okay, because a small amount of contamination will give an infinite slope to the driving force for the impurity to mix. With the pure compound, right. So I am always bound by 5 nines, right. So the more nines I have to make of purity, the more costly it is, right. So it is easy to make 99.999% pure, but if I have to add the couple of other nines, then it will be more costlier, right. So my processing should involve even further runs of just purification, right. If I have to make it even more pure, then so I am just dying, right. So it becomes much more costlier, right. So the number of nines you put in terms of the purity, the costlier these materials. I gave you example of gases, but the same thing is true with wafers, silicon wafers, right. we said silicon wafers are made through what is called this CZ process or Czechoslovakia process, right? Czechoslovakia process. Okay. So, we will look at how silicon wafers are purified using what is called a float zone technique, right. So, we will look at that as one of the case studies, but so the more you purify it, the harder it becomes to make it finally that adding that additional 9, right, the much more exponentially harder it gets. Okay. So, of course, you will have some purity percentage if I am not intentionally doping it. Even if I say silicon is intrinsically pure, I am saying that it is only 99.999% pure, right. So, there will be some carbon, some impurity that it has taken from atmosphere, and it has just become so it's impossible to make it completely pure, 100% pure, right. So because because there is a thermodynamic reason for it, right. So x2, so you can always say, look, you are telling me G versus x2, you have a control over x2. Yes, x2 is a controllable parameter, right, but especially if x2 is 1, right, there my controllability is not very so very much, because so there is so many trace elements in the atmosphere, and so this has so much of propensity, infinite propensity to take any of these trace elements and come down, right. So my controllability is affected, especially when I go to x2 equal to 1 or x2 equal to 0, right. At other places, okay, I have a finite slope, so I can control what x2 is, okay, so within some error margin, right. But especially at x2 equal to 0 or x2 equal to 1, the slope of this ideal mix goes to infinity. So, even if I have a small error, right, so even if I have some small impurity trace ppm of impurities, right, ppm is parts per million, ppb is parts per billion, that is lesser. Okay. So, x2 comes in and my impurity comes in, and so I will not have my pure material anymore, right. So, that is just fact of life. We have to live with it, right. So, everything wants to mix to a certain extent at least, right. So, there is nothing called a pure material, everything wants to mix, right, and that is just fact of life, we have to accept it. So, we have to accept that we will work with 99.99999, 5 nines is good enough purity for me, right. So, we have to accept the fact that my silicons are not 100% pure silicon wafers, there will be some carbon, some trace thing that has just got into the crystal structure, but I am okay. As long as it is not affecting my electronic properties, I am fine with it. Okay. So that's so that's the message here, right. So the thermodynamics, so the solution thermodynamics has already given me a message that, look, you want to form 100% pure compound with, you think you have complete control over composition? No, think again. Especially at the poles, right. So at this pole and this pole, so you have an issue. Okay. So at other places maybe you can manage with the errors, but at the poles you have an issue because it goes to it goes to this value with infinite slope. Okay. All right, good. So then now what so we have let's get back to this G ideal mix. Okay. So G ideal mix is I said it is KBT x1 ln x1 plus x2 ln x2, right. Now G is nothing but so what is G? G comes from some kind of an entropy plus some enthalpy, right. So I am just going to say G is enthalpy of mixing plus entropy of mixing. The reason why I am introducing enthalpy and entropy again is I understand my bonding, right. So I understand how my atoms are arranging, right. So now I am going into more atomistic picture, right. So by looking at entropies and enthalpies, right. Okay. So G ideal mix is H ideal mix minus T S ideal mix. So this is the definition of G, right. So let us go back and then try to see what this means. Okay. Now what did we say was S ideal mix from G ideal mix? S from G just comes as dou G by dou T, right. So that is S, correct. Now if I take so S ideal mix is just going to be KB times x1 ln x1 plus x2 ln x2. Okay. then I also ask you to find what H ideal mix is, right. So, you can either use this expression, right, to get H ideal mix, or there is another expression which I did not really pay much attention to, but H from G can just be written as H equal to dou G by T by dou 1 by T, right. So, you can show that these two are equivalent, right. So, from the enthalpy is just dou G by T by dou 1 by T, right. So, this also has a name, I forget what the name is, but this is an expression, okay. So, this is a well known expression, alright. So, now what is dou G by T by dou 1 by T? That is equal to, so when I do dou G by T, I do not have any temperature dependence, so that is equal to 0, okay. So, in an ideal solution, right, the enthalpy of mixing is 0, right. So, the mixing completely originates from entropic factors, okay. Now, it makes sense, right. So, entropy wants to mix things up, right. So, this is pure compounds are not possible means, so because I want to increase the entropy of the system, right. So, entropy wants to mix things and create many states and things like that. So, so the ideal mixing, so ideal solutions can form solutions only because I have some kind of an entropic stabilization, right. So, this is called the stabilization of the solution comes from entropy, okay. Now, what was this entropy of mixing? Entropy of mixing we said is Kb times x1 ln x1 plus x2 ln x2, okay. Now, can I, so I can look at this in many other ways. So, I have N1 molecules of species 1, N2 molecules of species 2, right. I want to just, so what is the entropy, right. So, essentially, so I want to mix them and tell you how many states are there, how many different ways can they mix, right. So, in how many different ways can N1 and N2 mix, okay. So, so that so I have N1 and N2, right. So, different balls, and in how many different ways can I arrange N1 and N2. The problem actually boils down to in how many different ways can I arrange N1 and N2, okay. So, that is just N1 plus N2 Cn1, right. So, that is equal to N1 plus N2 factorial by N1 factorial N2 factorial, right. And the entropy is nothing but Kb times ln of this is W, ln W, right. So, this is the Boltzmann entropy. So, I can actually show that this is Kb ln N1 plus N2 factorial by N1 factorial N2 factorial, right. And there is a simplification. So, for large numbers, ln so n factorial can be written as n ln n minus n, okay. So, this is a simplification I can use, and I am going to say so n1 plus n2 ln of n1 plus n2 factorial by n1 factorial n2 factorial, right. So, that just comes out as n1 plus n2, that is capital N ln n minus n, right, minus, so that is the numerator, minus n1 ln n1 minus n2 ln n2 plus N1 plus N2, right. So, N1 that goes away, and what I have is, so N1 ln n by N1 plus N2 ln n by N2. N1 by n is x1, so that is so I am looking at capital S, but I can look at capital S by n, that is a specific entropy, and specific entropy is Kb times minus Kb times x1 ln x1 plus x2 ln x2. Okay. So, this quantity is essentially so I said this is the entropy of mixing, ideal mixing, but this is what is also called configurational entropy, right. So, I just put two species in combination with each other, just to increase the entropy I have to mix, right. And how many number of states am I creating by I mix and I can create all these states, and that is what is telling me what is the total entropy of the system. Okay. So, the mixing does not need to be that atom A is interacting and forming a bond with atom B, atom A likes atom B, no, just entropy. Entropy will prefer mixing, right. So, just so this is entropic mixing or configurational entropy. I shower in 20 atom A's, I shower in 20 atom B's, I put them close to each other, so there will be some they will mix eventually, and that is just entropic mixing. I do not need to invoke any sort of bonding, A wants to bond with B, even if A hates B, entropy would want A to mix with B. Okay. So, even if oil hates water, you can see some oil molecule, some very little, some teeny, so at some nanometric scale, they can mix entropically, right. So, entropy will always prefer mixing, right, or forming solutions, right, until the other factor, right, until enthalpy prevents it, entropy will always prefer to form solutions, right. Anyway, so this is what we derived from StatMech, and this is what we got even from SIM, right. So, entropy of an ideal mixture is also exactly Kb times x1 ln x1 plus x2 ln x2, and my entire GIM is coming from entropy. Okay, which means in an ideal solution there is no or enthalpic mixing equal to 0. Okay. Now, what is enthalpy, right? What is enthalpic mixing? Okay. I have, so I am going from a pure compound that has only A bonds, right. So, A, right. So, I have a causal crystal of A, sorry, A, right. So, I have only A bonds, right. So, this is a pure crystal which has only A bonds, right. I have another pure crystal that has only B bonds, right. Now, what defines enthalpy? Enthalpy is, so if I have to break a bond or if I have to form a bond, enthalpy AA, right. So, the energy released when AA bond is formed. okay, or energy spent to break an AA bond. Right. So, this is the formation energy, right. Similarly, epsilon BB is energy released to form a BB bond, right. Now, there is another type of bond, right. So, now once I put A and B together, I will get AB, right, or 2AB essentially, right. So, where A B, B A, B A, B, okay, A, okay, A B A B, right. So, now I am forming AB bonds, right. What is the energy of formation of AB bonds? That is epsilon AB, correct. Now, what is the enthalpy of mixing? Enthalpy of mixing is the enthalpy of this reaction, right. So, I am actually so going to make my AA and BB into AB, 2 times AB, right. So, 2 times epsilon AB minus epsilon AA minus epsilon BB, that is the enthalpy of mixing, right, per unit atom, right. So, per unit atom, okay. So, the units are EV per atom, okay. So, that is the enthalpy of this reaction essentially. So, I am taking pure compounds and I am making AB, right. So, I am making a solution of AB, right. So, enthalpy is just 2 times AB minus epsilon AA minus epsilon BB, right. So, now with this definition of enthalpy, when I say that enthalpy of ideal, this is enthalpy of mixing, sorry, H mix, right. So, when I say enthalpy of ideal mixing is 0, that means epsilon AB should be equal to epsilon AA plus epsilon BB, right, or it should not matter whether A bonds with A or A bonds with B, right. So, A likes both itself and B equally, right. So, there is no differential liking, right. So, sometimes it happens that A hates itself, A hates another kind of itself, right. So, A would always want to homogenize, A would always like to diversify, A would want to find B, right. So, in that cases epsilon AB, right, is greater than epsilon AA, means A likes B more than A likes A. Okay. Similarly, if epsilon AB is less than epsilon AA, which means so when A comes and bonds with A, it releases more energy, which means it likes A much more than it likes B, right, means A likes itself meaning one of its own kind, more than A likes B, correct. But in this case, in an ideal solution, you are saying that A likes B as much as A likes itself, okay, or B likes A as much as B likes itself, right. So, or B likes A as much as B likes itself. So, in other words, epsilon AA equal to epsilon BB equal to epsilon AB, okay. So, that means that 2 times epsilon AB minus epsilon AA minus epsilon BB equal to 0. So, I have no preference, right. So, whether if I put A and so molecules of A and molecules of B together, bonding wise I have no preference, right. So, A can either bond with A or A can bond with B, right. So, enthalpically there is no preference to either mix or segregate, right, but it will mix because entropy will want it to mix mix and make some optimal random configuration into a random solution. Okay. So, A's and B's are mixed in a random fashion, right. So, let us see what randomness is in the next class, but A and B wants to mix in a random fashion and form a random solution. Okay. So, this is just entropic stabilization. So, what are the examples, right. So I want species that like each other equally as they like themselves, right. So, let us take isotopes U238 and U235, right. They are just different in nuclei. Right, but their chemistry is similar, right. So, epsilon U 238 U 235 will be the same as epsilon U 238 U 238 will be the same as epsilon U 235 U 235. So, this is so if I put U 238 and U 235, be assured that there is only entropic mixing. Okay. So, that is the simplest case, right. So, but I gave you other examples of so HFO2 ZrO2, something like platinum palladium no sorry platinum I will write it for now, but I can check this later, right. So, platinum palladium, right. So, these will mix in an ideal fashion, these will form ideal not absolutely ideal, but ideal like solutions, they are good enough to form ideal solutions. Okay. And I want you to understand, so what so the question is what factors determine whether A and B will mix ideally or not, right. So, there are a set of principles on thumb, right. So, typically if you talk to chemists, if you talk to material scientists, they like simple things, right. So, I want to be able to count things on my fingers and I want to say look, it is simple, right. So, if I have atoms of the same size, maybe they will bond together. If I have atoms of similar electronegativities, right. So, their epsilon, they will like each other similarly if they are similar in a lot of if they are quite similar, right. So, quite similar means what? Quite similar means their sizes should be similar, their electronegativity should be similar, their charge state should be similar, right. So, as long as I do not see too much of a difference, I am not putting carbon in conjunction with something much bigger, or I am not putting hydrogen in conjunction with titanium or something like that, they will mix, right. So, be wary of the fact, right. So, if I have two similar atoms, right. So, I go to periodic table, I take some metal platinum and I take just the metal right next to it and see so they have similar sizes, both of them will form metallic bonding, both bond similarly, right. So they have to so if I make a solution out of it, it is more or less likely that they will form an ideal solution. Okay. So, there are set of simple principles, and these simple principles are what are called Hume-Rothery rules. I will not give you all the rules in this class, I want you to go back and check what these rules are, right. So, Hume-Rothery rules, check these rules, okay. And Hume-Rothery rules tell us when two materials can mix nicely and easily, and that essentially means how can they form ideal solutions and whether they can form ideal solutions, and these are guiding principles. This is not even, I mean, I can violate Hume-Rothery rules, no problem, but more or less so lot of materials will, if they if they conform to these rules, they will form ideal solutions, right. So, the atomic sizes should be similar, the ionic sizes should be similar in ionic compounds, right. The electronegativity should be similar, right. So, these are two of the rules, but there are a few of them, right. So, I want you to go back, read them up, right, and try to intuitively understand, right. So, it is all now very simple chemistry like you did in your 10th standard, 11th standard, right. So, where So as I keep going down in periodic table, oh, the size increases or size decreases because I have more nuclei, I mean, or as I go right side in a periodic table, the size decreases because I have more protons in the nucleus, and then and so the electron clouds will shrink, right. Simple intuitive principles, right. So intuitive principles, more than physicists, I would say chemists and material scientists think of intuitive principles. Can I understand it in a very intuitive fashion, right? Then we will put in the math, then we will complicate things, no problem. So that is what we have been doing so far. But intuitively, can I understand whether given two materials will they mix and form a solution like water and sugar, right? And what are the possible features at an atomic scale that I need for these two materials to mix, okay. So they go by the name Hume-Rothery rules. Maybe in the next class, if you were taking my class, I would have asked you to tell me what these rules are, but in the next class I can sort of narrate. But so you take a pause, look up what those Hume-Rothery rules are as a self-study assignment, and then you tell me so you convince yourself how it makes sense, okay. So intuitive sense, you should get some intuitive picture. Material science is all about feeling, right, a lot of it, not all, of course there is mathematical rigor, but so once you have the feel, you can design your experiments, so it's important to get that feel, right. So you have to feel the materials, okay. All right. So with that, let us end here, and then let us start with Hume-Rothery rules, and so entropic stabilization, ideal solutions, but then we will start adding non-ideal solutions, and we will look at what happens when enthalpy comes in, right. Enthalpy will either stabilize the so called disordering or solutionizing, or it will destabilize the solutionizing, right. So we will have to see how enthalpy will compete with entropy, and then do all the magic tricks that it is going to do for various solutions, okay. And then we will be in a stage to construct the phase diagrams, okay. So with changing compositions, and pressure and temperature we have already done, but now we will change compositions and we will be able to construct phase diagrams, right. So we will understand some simple models, and then so in any phase diagram we are going to invoke these models and say, oh look, this material hates this material enthalpically. So at high temperatures I have entropic stabilization, they mix well, but at low temperatures enthalpy takes over, right. So I am going to use these sort of arguments, right. So despite seeing very simple models, the arguments are going to be based out of these simple models. But so the models from system to system can get more and more complicated. Then I have to calculate what these are using thermodynamic calculations and simulations, okay. So but let us not go there, let us try to get an intuitive picture of all these phase diagrams, okay. So that's those are the exercises that we will be doing from the next class onwards, okay. And thank you very much. I will see you again in the next class.